So today we have our third workshop. We do not have a lot of people, but I hope that the most of participants will see this workshop in the record. So today I will share my screen. So today we will speak about different type of satellite images. We have already learned a little bit about how to deal with satellite imagery online. We have tried different online tools to access satellite images, but let us now, today we will speak in a more general terms, like what are actually the main types of satellite imagery, how different satellite images are different from each other. And we will start from very general thing, from the types of orbits satellites could have. First of all, you know that satellites are circling around the Earth on certain type of orbit, and this orbit could be circular or elliptical, generally saying. So by form, it could be different. Of course, for remote sensing satellites, which are targeting to observe Earth, the elliptic orbits are no good, because the distance from satellite to Earth will be different, and also the level of details, the resolution of images will be different. And so most of the satellites are in circular or near circular orbit, if you are talking about Earth observation satellite. Also, there is an orbital parameter called inclination. It means the angle between the equatorial plate and satellite orbit. In principle, of course, in general, could be the satellite could orbit around the Earth over its equator, so it will be equatorial orbit, or could be totally different on the polar orbit, like that. So if the satellite, each circle makes over Earth's poles, northern pole and southern pole, then it will be polar orbit. And also it could be so-called inclined orbits, which could be any different angle between equatorial orbit and polar orbit. Of course, if you if your satellite flies on the equatorial orbit, it mainly will observe the areas along the equator. So for such a satellites, it is very difficult to see any details in the areas close to poles. So the most of the Earth observation satellites, they have polar or near polar orbits. Also, we could mention there could be two special types of orbits, and one is so-called geostationary orbit, when satellites is orbiting Earth on the equatorial orbit, but with the same speed, the same rotation velocity as the own Earth rotation. So it means that the satellite all the time is looking at the same site, at the same point on the Earth. So it is somehow, we could say that it is hanging on the Earth. Of course, the geostationary orbit, they must be equatorial because that's the only way to be over the same point on Earth, and also to make the whole circle in the same time as about 24 hours as the Earth does it. So the satellite should be located at a pretty high altitude. It is over 35,000 kilometers. So it is a very high orbit. Let's say, for example, the International Space Station is located only 400 kilometers over the Earth's surface. And for a geostationary orbit, it must be nearly 36,000 kilometers. So it is much, much far. And of course, being on that very high orbit, the satellites cannot see usually any details on Earth. There's just one example. This is a photo from a geostationary satellite. This is a Russian Electra-L. American satellites also, there are some geostationary satellites, geostationary American satellite like GEOS, which could see the whole Earth at once practically. So, but we do not see actually any details here. Over time, the satellites will see the same size of Earth. So this is not very common that the Earth observation satellites, remote sensing satellites, they are on the geostationary orbit. The most common case and actually very profitable for Earth observation is to place the satellite in the so-called sun-synchronous orbit. It must be polar or near polar. And the trick is that satellite is orbiting the Earth usually at a not very high altitude, like 600, 700, 800 kilometers. But each time it flew over the sunlight side of Earth, it crossed the equator about usually approximately at the same time, local time. So each time it crossed the equator, like for example 10 a.m. So because while the satellite is doing the circle around the Earth also rotates under it. And the next location, the next crossing point of equator is done at approximately at the same local time. For example, like the most of Landsat satellites also have that type of orbits. Like for Landsat from early Landsat satellite series like Landsat 1, 2, or 3, they usually cross equator at 9:40-42 each time, each track, each pass over Earth on orbit. The local time of crossing the equator is the same. So it means like the most of the time the satellite is looking on the sunshiny part of Earth. Of course, when it is descending pass on the other side of Earth, it is a night side. But on the day side, it usually flew over every location approximately the same local time. So the sun angle, for example, and cloud conditions usually will be the same. And so this is pretty convenient. And this is why the typical orbit of remote sensing satellite usually is there are many exclusions, of course. You have seen this geostationary satellite image. But usually, in the most typical case, the orbit of Earth observation satellite is circular or near-circular. It is usually near-polar, and usually it is sun-synchronous. There is even division between different satellites that sun-synchronous satellites could fly over daylight side of the Earth in the morning or in the noon or in the evening. So it could so-called morning satellite or midday satellite or evening satellite. The most of medium and high resolution satellite we will deal with, they tend to be adjusted for morning flyover. So usually the altitude for remote sensing satellites are not very high. So it is not very high orbits like geostationary or some communication satellites. Usually the orbit is pretty low. This is so-called low orbits. Usually 500 to 1,000 kilometers. And also the inclination, as I told, is very high. So it is near polar orbit. And usually the period of rotation around the Earth is just about 100 minutes, an hour and a half approximately. So it means the altitude is so low, not only because of a few reasons, and one is this to fit these conditions for synchronous orbit. And also another is to be as close to Earth as possible. You cannot be too close, otherwise the Earth's atmosphere will decrease the speed of the satellites, so the orbit will be not sustainable. But at the same time, you should not be too far. So the closer you are, the better, but not too close to have a sustainable orbit. And this is why the altitude of remote satellites orbits are usually like that. For example, this is the orbital parameters for Landsat 8. For example, this is a typical remote sensing satellite, which is located in sun-synchronous orbit, and equatorial crossing time is nominally about 10 a.m. So this is of course not precise. It could a little bit vary of local time, and the altitude is 705 kilometers, and the inclination is a little bit even over 900, so it means like it is near polar orbit, and the rotation is about 100 minutes. Yes, you could. There is a question. You could speak. You could just switch on your microphone, and you could speak. If you have a question, just ask. Okay, if it was just occasional, just no problem. But if you would like to ask questions, you could just do it. Just raise your hands and ask questions. And also important is repeat coverage. So it means that circling around the Earth, the Landsat 8 will return to the same position, to same path, once in 16 days. So in 16 days, it will come back to the same orbit, to the same location over the Earth's surface, and could shoot the same place. So what now from satellites to the images they produce, and the main characteristics of satellite imagery are the following. First of all, it is a spectral resolution. We will now just go through and then we'll talk about this in more details. Spectral resolution is basically the size of a pixel of an image representing the size of a surface area. So how big, how large surface area is represented by every pixel. Also important is the swath weight, so the weight of a stripe on the surface area covered with a single pass, single flyover by satellite. And also we could tell about so-called temporal resolution when we mention, for example, repeat coverage 1 in 16 days for Landsat 8. This is a kind of temporal, we could call it temporal resolution. So this is revisiting period, the time before the repeat coverage of the same area. Also, I will briefly mention about spectral resolution, which we have already discussed in our previous meeting, previous workshop, this number of spectral bands. And also, there's also such a, images could be different by radiometric resolution. Basically, it is a bit depth of a sensor. So how many bits is used to code the color for each pixel. So it just defines the number of recorded level of brightness. So how many level of color that sensor could record. And also we could, in the end today, I could briefly mention about the radar sensor type, which is different from the optical sensors which we have discussed so far. Now, first of all, I think the spectral resolution is the most important characteristics of every satellite. So, and basically, he is important of how big areas is covered with a single pixel. For example, here in this first slide, we see the high resolution image, which is one of probably it is already not operating, QuickBird satellite, which has a 2.5 meter resolution per pixel. So every pixel represents on the ground the area like 2.5, 2.4 meters for 2.4 meters. So it is just a few square meters. And as we could see, this pixel is smaller than the size of a single tree usually. So each tree could be represented by a few pixels even. And here is another example. This is a Landsat. This particular is Landsat 7 image, where the size of a pixel projected on the ground is 30 by 30 meter. So each pixel of Landsat somehow generalize the light, the reflected light from a number of trees for pretty relatively bigger area, and show it with only one pixel. Let us see how could it looks like. For example, I just took this picture from Google, which employs the high resolution images. Probably here in this particular area, it is a WorldView 2 satellite. And it has a pretty high spatial resolution. So each pixel of WorldView 2 image is 50 by 50 centimeters. So you could see many details. Practically, you could see every branch in the tree. You could see some open space, some roads in the forest. And I placed here over the this red and yellow rectangles. So the yellow square is the pixel size of satellite Sentinel-2 satellite, 10 by 10 meters, and the red two red squares are the boundaries of a single Landsat 8 pixel. So we could see that, for example, Landsat pixel could cover not a single tree, but a group of trees. And let us just see the same area. If we will, for example, place here the Sentinel-2, approximately the same season, and hopefully the same time, the same year, you could see that every pixel has different color. This, of course, it is again, this is the so-called false color. So this is a synthesis of 2 infrared and 1 visible red bands. And we could see that every Sentinel-2 pixel generalize the signal from many different objects on Earth. For example, here, if you could step back and see this open space in the forest, maybe it is a kind of football field or whatever. So you could see the Sentinel pixels here are different, but also some pixels could be on the edge of this open space, and so they generalize the signal from grass and from trees. So they could be of different colors, like more lighter and more darker. Also, you could see that different type of trees. For example, in the upper part of this image, you could see some red or at least some darker green and a bit reddish pixels, which represent the coniferous tree or some areas in the forest which coniferous tree dominance. And here we could see even more coarse picture with Landsat Spectral Resolution. We also could see that different pixels somehow have a different color, different reflections from Earth in this area, but each of that pixel generalize the reflected light from different objects on surface. So for example, for each Landsat pixel in the red boxes, the signal is somehow summarized from different type of trees, from part of open grassland space. And so you cannot see more details than the size of a pixel. So you cannot see in the image the objects which are smaller than the pixel size, or even if they are comparable with the pixel size, it could be problematic to see it. For example, in this particular area in the right lower corner, we could see this open space in the forest, the grass, patch of grass in the forest. And here it is represented practically with 1 pixel and a few pixels which are partly affected by the reflection from this grassland. So here in Sentinel-2, there is already enough pixels to at least to guess or maybe even delineate the boundary, approximate boundary of this grassland patch. And only with a high resolution, you could make this boundary more or less precise. Here you could do it approximately with Sentinel-2, and with Landsat 8, you could only guess. So this is the object which is too small. So even objects must be even not just 1 pixel, but usually it must be larger than 1 pixel. It should include a few pixels to be visible in satellite images. But of course, it does not mean that the coarser resolution is worse than finer resolution. It depends on your task, on your goals of your observation. Quite often, it is much more important to see for example, the forest as a whole, rather than a single tree. We even have a Russian idiom, to see the forest behind the trees. This is exactly the case. So to see something more general, not to be lost in the details. So there's also different types of images, different types of sensor. They have different spatial resolutions, and there's very not very well defined classification, which also could be changed over time. Nowadays, as a very high resolution is regarded everything which has a resolution finer than 1 meter per pixel. So all these, the most of images you could see in the Google Earth or Yandex Maps are basically of this very high resolution. Also, there is something called high resolution, something between 1 and 10 meter per pixel. And the most of images we will deal with are usually of so-called medium resolution. Previously, it was called high, but nowadays it is regarded as medium already, from 10 to 30 meters per pixel. And also there is a number of satellites equipped with sensor with pretty low resolutions, which many of them are also publicly available, provide its data online, so you could see them. And also sometimes some mainly meteorological satellites, they are called like very low resolution images or very low resolution sensors, which could be hundreds and even some thousands meters per pixel. Just to show you again some examples, I think you have already seen some examples of satellites with different resolutions. For example, this is GeoEye image of very high resolution below 1 meter, and this is similar to the images you could see in Google Earth and Google Maps and Yandex Maps, for example. There's just another example with a European Union French satellite called Spot. It is not operational anymore. This is a Spot 5. Now they have newer satellites of that series. Here you already cannot see that level of detail, so you hardly see single cars here, for example. But generally, you could see some buildings, some roads, some landscape elements. You could see details of like tracks on the croplands, the tracks of a machinery. You could see some. You can, of course, cannot see single trees, but you could see generally different details in the forest and so on. Very similar resolution, but a little bit coarser. They has Sentinel-2 satellites, which is basically the same area I showed you as an example. You could see this in the center, 2 small red square, which represent this Landsat pixels, which I demonstrated in the previous slides. So this is a area close to the edge of the city of Moscow. You could see also some forested areas, forest tracts, and some built up areas. You could see single buildings, mainly big one. The small one is not really visible. You also cannot see, as we already learned, single trees, but we could see many different stands in the forest. You could see the difference between coniferous stands, deciduous stands. You could also quite clearly see the roads. This is also Moscow Beltway, for example, the biggest roads. You could even somehow guess that you see the cars, but actually you do not see any cars exactly. Next level, the same area in Landsat 8, I zoomed it a little bit in, so you could see again even less details. Generally, you could even single buildings you usually do not see. You could only see the built up area in general. And also you could see different forest types at some coarser scale. Just another example of Landsat from another location, more southern area, where you could also see different types of croplands. Some of them are just have bare ground, and some have some growing crops on them. And generally, you also could see some populated areas, some built up areas. In the center, you could see also then different type of logging in the forest, but you do, of course, do not see any further details. And this is example of low resolution satellite image. It is taken from Terra satellite instrument, the radiometer instrument sensor called MODIS. This is a multispectral radiometer, which records many different spectral bands at pretty low resolution. So you only could guess here somehow to separate agricultural lands from forested areas. You could see the river, open water, or in the closer to the center, a little bit on the right and down from the center, you could see the burnt area, the fire scar, the track of ground fire. And by the way, this low resolution is of course, you cannot map any details, any small objects and any detailed maps with it, but generally many, for example, forest maps or vegetation maps are produced using that type of imagery, especially if you are mapping like the whole country or the whole continent or the whole region. This type of imagery is very useful for vegetation mapping. And this is example of a low resolution satellite image, which is just 1 kilometer per pixel. And this is from meteorological satellites called NOAA, NOAA. This is an American satellite used for mainly for meteorological observations. And of course, you cannot see any details, but here you could see at the same time the whole European part of Russia in one shot, practically from Black Sea to Baltic Sea in the north. And of course, you cannot see, for example, any vegetation details or anything else, but you could observe this, for example, clouds and this cyclone, which is very important for Earth forecast, for weather forecast. And this is actually the main application of this imagery, when you could see how the atmosphere and cloudness, how does it move over time. And this is also pretty important. And just maybe this extreme case again, I have showed this image to you already. This is a extremely low resolution image, which feeds the whole planet at once practically. And of course, you do not see any details here, but again, you could see some cloud movements and other weather phenomena here from that distance. It is done from nearly 36,000 kilometers altitude, so it is very low details here. And of course, different various resolution are used for various purposes. Like for fire monitoring, usually the even low resolution is enough, and you are watching the large-scale events like with smokes from fire or with large landscape fires like in Siberia. So if you are monitoring forestry like logging plots, it is enough to have medium resolution images like Landsat or Sentinel are very suitable. Of course, you will not see any details in a particular logging plot, but you could see the general location of logging, the road system, development over time, and so on. And if you are looking for some very small changes, like for example, this illegal logging in tropical forest, where illegal loggers just remove single trees or a few trees, when you need the really high and very high resolution images to spot this activity. So also another important moment, another important parameters is a swath height, the height of a stripe shooting from satellite over single pass. And with the same resolution satellites, sometimes the height of this stripe could be pretty different. Actually, Landsat satellites, Landsat images, they are in some extent unique, that they have pretty wide swath, pretty wide stripe, as wide as 185 kilometers. So you could cover the whole area at once, pretty large area at once, not to use many images together to map the large area. Also, different satellites, they could have very different swath height. Like Terra Modis could be over 2000 wide, and high resolution satellites, they usually have pretty narrow swath. They could only shoot very narrow stripe at once, usually by request, open request. And of course, it does affect the area each particular satellite could cover during a certain time period. For example, these Terra Modis images from Terra satellites, this is just a shooting of one day. So you could see in one day it could cover the whole Eurasia and also part of Africa. But actually, the biggest part of the world is covered with these satellites in a single day. You could see these stripes, swaths, which have a height of 2,300 kilometers. And this is why it covers so wide area at once. But usually, whether we should to somehow look for a compromise between spatial and temporal resolution. And this is with Terra Modis and Landsat images. This is a very good examples. Here we compared the coverage for one day. This was in June 2014. In the upper part, there is a day coverage of single satellite Terra satellite. This is a coverage of a single day. You see practically the whole Earth surface is covered, excluding the Antarctic, because in June there's a polar night there, and there's practically no light to make optical photos, optical images. And two Landsat satellites together, Landsat 7 and Landsat 8, they only could cover these narrow stripes over landmass. So it only could, every Landsat satellite could produce the same coverage as Terra Modis in 16 days practically. You need more than 2 weeks for Landsat satellite to cover the same area which Terra satellite could cover in a single day, or sometimes even twice a day. So this is the result of this compromise, that you see that usually this is not a very common case, but usually when not a very strict rule, but generally the higher resolution the satellite image type has, the less frequent is the coverage. So like Terra Modis covers every day, Landsat once in 16 days. Sentinel, for example, there were 2 satellites, so they could cover practically every week, and so on. High resolution satellites, they usually do not shoot all the time, so they only could focus on some particular area and make a satellite image you can request. So the general productivity of very high resolution satellite is usually much lower in terms of area. And in the end, very briefly, I would like to mention also that we already discussed last time about electromagnetic spectrum covered with modern multispectral satellite sensors. And different satellites, you remember, they have different number of sensors and different parts of different bands. I would say different set of bands. They could actually use, like Landsat 8, for example, it has 11 spectral bands, and different satellites you could see also might have different set of bands. Like this, we have already seen this image last time, and we could only focus that, for example, Sentinel, it has maybe higher spectral resolution in visible in near infrared, but in general, it has approximately the same number of spectral bands as Landsat 8. But Landsat 7 and Landsat 5, they have less spectral bands. And on the opposite, this MODIS camera, the MODIS sensor installed in Terra and Aqua satellites, it has low resolution, spatial resolution, but you see it has pretty high spectral resolution. So it has very many bands, many of them pretty narrow. So they record separately each small portion of electromagnetic spectrum in this area. So in this case, we could tell that MODIS instrument, MODIS sensor, has the highest spectral resolution among these satellites. also we could already mention that depending on this swath weight and depending on construction of a sensor, the repeat coverage of different satellites could be different. I have already mentioned that. And in the end, I should maybe probably very briefly mention the radiometric resolution, because you see the same image done with the same spatial resolution could still contain less and more information depending on how many grades of shades of grades of colors, for example, how many gradation of gray in this particular case is recorded. How even not how many grades could be, how many gradations could be sensed in a sensor, but how many could be recorded and somehow transmitted from satellites to the Earth, because sometimes the quality of sensor could allow recording more gradations, but the bottleneck, the limitation is the radio channel, data transmission channel to Earth, and sometimes the engineers developing this remote sensing system, they just reduce a number of bits used for to record value of every pixel of the image, and so it makes the total amount of data sufficiently smaller. But it could affect, of course, the quality of the image. For example, in the left image, it's the same object, same time, same sensor. It is just we just artificially changed reduced the number of bits used for every pixel, and you could see that in this airport, you could see much more details if you use 10 bits per pixel, because we have more gradations of gray color here, rather than if you use 7 pixels, when it will be somehow too light or too dark, and some details will be lost. You just this radiometric resolution, the modern satellites, it is maybe less important, because in the most of a satellite it is high enough, so it could be in practically all satellites we will deal with, it is like 10 to 16 bits per pixel. So it is not common now to find some satellites with 7 or 8 bits per pixel. But just remember that, especially when you would like to somehow save your picture, your satellite image as a picture, for example, for presentation. And if you would like to reduce size of a file, then you could just try to reduce number of bits per pixel. And just remember that it could affect the quality of the image. So, and in the very end, I will just mention that before we mainly told about the so-called optical images, which are using that part of electromagnetic spectrum, visible and infrared light. But actually, there are also satellites which are equipped with this sensor, which could detect the radio waves. But this type of satellites, they usually work in a little bit different way. If you remember these pictures of optical satellite, this is how optical satellite works. It just also optical sensors quite often are called passive sensors. So they only passively detect, passively somehow accept, passively received the sunlight reflected from Earth, or emitted by infrared light emitted by warm surfaces, but it is somehow passive sensor. If we could imagine the radar satellites were constructed and designed in a totally different way, they are active. So in that kind of satellites, practically there are radars installed there. So the satellites will actively emit the radio waves towards Earth, and when sensors receive reflected radio waves. And so this, we will not go into details now, but just the radar, satellite radar images will look very differently rather than optical images. For example, this is an example from Radar 1 satellite, and this is an image from oil field in Western Siberia. And you could see that it is difficult to even to tell about colors here. This is a black and white image, and you just see that the radio waves were reflected the most strongly from some buildings. Is particularly you could see like here and here, you could see the oil reservoirs made of iron. So the iron and metal in general, metals, they reflect the radio waves the strongest. So you could see here this metallic installations on the ground. You could see the most bright white color, and the water, usually they do not reflect radio waves very well, and so you could see lakes here as a black spots practically. But also these radio waves, they could be reflected very differently, also from different shape of a surface. Also, particularly it was found that the radar images could be used to spot the oil spills on water, just because the surface of water covered with oil has a different shape rather than the regular waves on water. And the radio waves of certain lengths, they are sensitive to that shapes, and this is why, for example, these oil spills, this is oil spills on the Black Sea in November 2016, could be detected with radar images. By the way, these oil spills was found with satellite images by school students in 2016. Just analyzing these freely available Sentinel-1 radar satellites. This is probably the only radar satellite which is available for free, and we could also try to use it later on. Of course, for radar satellites could be used to track ships and ice on seas. Ships are very well visible because they are mainly made of metal, but also the ice on the northern seas is very well visible in radar images. And what's important, that cloud coverage, which is so problematic, which creates so many problems for optical images, for radio waves, the clouds are transparent, so you could see the Earth surface at any time, day and night, and at any weather conditions. So you could see through the clouds and see the surface, see some situation, for example, on seas. You could follow the ships going overseas. You could also find out some other metal objects, and you also particularly you could monitor ice movement in the northern seas, and this is also quite often used for that purposes. And also, as the radio waves are very sensitive to the shape of the surface, they are widely used to make the digital elevation models. So to map the relief, to map the elevation of the Earth surface, and actually it is usually with radar sensors, they're usually pretty sensitive to detect any changes of surface. If, for example, part of a surface just landslide because of landslides of some, for example, karst phenomenon, that some changes in the surface they could be detected. This is also used, for example, to measure the volume of ice in glacier in Antarctica, and to see how this not only the area covered with ice, but also the volume of ice, how it is being changed. So this is what the radar satellites could be used for. But of course, this is a very somehow brief overview of radar images, but we just have to remember that this is the images of a very, very different type, especially because they are the satellites are using active radar, actively sending radio waves to the Earth to detect the echo, to detect the reflection. So I will stop here because we have running out of time. So if you have some immediate questions, you could ask right now. If not, you could also write to us anytime. We will try to reflect. We have so far received some home tasks done by some students also attending today, but not for everyone. So we are still waiting for previous task to be done. So any questions right now? If not, I would like thank you everyone for attending today, and hope to see you soon again. The record will be available of this meeting, and the presentation will be available as well. Just in a couple of days, we will share it. Thank you. See you again.